I don't know if I put the full screen, we will be able to see there's another map. I don't know if you'll be able to see. So we have transformation, and what is a transform? Yes, some students are still coming. Let me admit them. And they're still coming. I don't know whether we can start at 8:40. They're still coming. Let me just give them 2 minutes. We start at 8:30. We can start while admit them as they come. So I was talking about transformation and what is transform. The transform is just to change or convert from one form to another. If it's a shape, you can convert that shape, if it's a rectangle or a circle, into a different or a new shape. And why are we doing this? Remember, we are discussing computer graphics, and we said that is drawing graphics or pictures on the screen or using this computer system or this electronic device so that they can be displayed on the screen. Because you can just pick a pen and start drawing on the screen. So when you are drawing this using this system or this program, you need to maybe some you need to convert or to change some shapes into a different form or a different shape, and that's why we are going to look at the transformation. Design applications and facility layouts are created by arranging the orientations and sizes of the component part of the screen. Changes in orientation, the size, you can change the size of the shape or a picture or that graphic that you want to draw, and shapes are accomplished with geometric transformations that change the coordinate description of objects. The basic geometric transformations are, and we are going to look at these types of transformation. We have translation, we have rotation, scaling, reflection, and shear. Just a minute, there's a student who have come. Let me admit him or her, or some students. So these are the basic geometric transformations. So we have translation, rotation, and scaling. You can scale, you can translate, or you can even combine all these: translation, rotating, and scaling. So we have 2D transformation or two-dimension transformation. Given a point, cloud, or polygon, or sampled parametric curve, we can use transformation for several purposes. You can use it to change coordinates frame. That is world, window, viewport, device, etc. So we have the world system coordinate, we have the window coordinates, we have the viewport, we will look at them, and the device. So we are saying that you can use this to change coordinates frame. Then compose objects of simple parts with local scale, position, orientation of one part defined with regard to other parts. You shape of a picture or a graphic, and it changes completely. If it was a circle, you can change it into a triangle. So you change the shape completely. What you are calling, you use deformation to create new shapes, or useful for animation. You can still apply this in animation. There are three basic classes of transformations. So we have these categories. We have rigid body, and under this, it preserves distance and angles. So the distance is not going to change in the angle. An example, we have translation. We'll see what we mean by translation, and rotation. Another category is conformal, that preserves or which preserves angles only. An example, we have translation, rotation, and uniform scaling. A pin preserves parallelism, lines remain lines. Example, we have translation, rotation, scaling, here, and reflection. So let us look at the types of transformation, and we have mentioned them. Let us discuss them. So the first one is translation, and this is where you change or you change the position of the shape or the graphic of the picture, so from one place to another. So when you want to move that shape, you can use translation, uh, translation, or you can translate that so that you can move from this place to another. And we use that. We have a matrix that we use to get the point or the new point. Like we have point A. Point A is x, y. So we are going to use this type of transformation, what we are calling scale translation. And now our new point, maybe P prime, where we have x prime, y prime. So we are going to multiply our original or our point P by the matrix, so that we move that. If it's a line, we move it from this position to a different place. So we have the translation by vector. So we have this T, or we have T1 or X1, or the point. Then we are going to translate, and we just use this matrix. So we are going to add. So if we have x, our point is x and y plus the matrix, and we get the new coordinate. So if our coordinate was 0, 0, x is 0, y is 0, you use that matrix. So plus, so if it was maybe 0 plus 1, we are going, the coordinate, x coordinate will be 0, 1, and maybe y will be, so it's going to move from 0 to 1. The point which we have this coordinate x and y. And you can see that diagram. This is the xy point, or this is the original shape. And when we translate it, it moves to this point. Translation moves every point a constant distance in a specified direction. Then the other one is rotation. And rotation is a process of rotating an object with respect to an angle. Let me admit some students. So the other one is rotation. And we are saying that this one is going to rotate an object with respect to an angle in a 2D plane. So it's a transformation in plane or in a space that describes the motion of a rigid body around a fixed point. So we have a fixed point, maybe 0.00, or p, the coordinate are 0, so the object is going to move around a fixed point. So maybe it's going to, if it's 90 degrees, it's going to move from 0 degree to, and it's going to go, if it's clockwise or anti-clockwise. But the position 0, is not going to change. So we have this, let me just admit that we don't have time. So we have this rotation. We rotate clockwise by beta, Argo beta. So we have point P. So we have the point P plane, or the new coordinate. So we are going to multiply by this matrix. So we have the matrix, we multiply by the P0. And we are going to get the P1 or the P prime. And after multiplying by that matrix, this is how this object is going to move. In 2 dimensions, only a single argo is needed to specify a rotation in 2 dimensions, the argo of rotation. To carry out a rotation using matrices, the point, maybe P0, X, Y, to be rotated is written as a vector, then multiplied by a matrix calculated from the angle beta, like this. So we have this is P0 or P, then we have the P1 or the P prime. These are the coordinates for the P prime, X prime, Y prime. So these are when we multiply by this point by this matrix, so this is what we are going to have, where x, y are the coordinates of the point after rotation, x prime and y prime, after we multiply by that matrix. And the formula for x prime and y prime can be seen to be this. So x, the x prime or the x1 is equal to x cos beta minus y sin beta after multiplying by the matrix. Then we have x prime, y prime is x sine beta plus y cos beta. Then we have the other type of transformation is scaling. And scaling, you either the shape or the object, the shape of the object is going to to increase or decrease. And we have two types of scaling. We have uniform scaling, and the other one is non-uniform scaling. So we are saying that scaling changes the size of an object. Either it can increase the size of an object or decrease the size of an object. The operation is achieved by multiplying each vertex or each point vertex coordinate xy by a scaling factor. So we have a scaling factor that we are going to multiply our coordinates or the point so that we get the new coordinates. So we have uniform scaling. It's a linear transformation that enlarges or increases or shrinks, diminishes objects by a scale factor that is the same in all directions. So we have this uniform scaling by scalar. So we have this. So you can have here we have A, or you can even have S1 and SX or SY, or you can even have DX, DY. But here we have A. So this is the scaling factor. So you multiply by the original, the P prime, or the original object or the set. Then we have non-uniform scaling. Is obtained when at least one of the scaling factor is different from the others. A special case is directional scaling or stretching in one direction. So non-uniform scaling changes the shape of the object, e.g. a square may change into a rectangle or into a parallelogram if the sides of the square are not parallel to the axis. The angles between lines parallel to the axis are preserved, but not all angles. So we have matrix representation. A scaling can be represented by a scaling matrix. To scale an object by a vector like the points, we have V is equal to into bracket dx, dy, dz. Each point would need to be multiplied with the scaling matrix, and that's the point. It can be P, so P0, and we are going to have this P prime. And to get this, we are going to multiply P0 or the odd P or the odd coordinates by the matrix or the scaling factor so that we can get the new coordinates, what we are calling the P prime or P1. And we have that scaling factor or the matrix. And when we multiply by that, this is what we are going to get. So our P1 or the P prime, so the coordinate will, after multiplying this original or the odd coordinates by the this matrix, we are going to get these new points. Like now we have dx, dx, dy, dy, and this P. When you call it the P prime, B prime and P prime. Then the other one is reflection about the y-axis. What do we mean by reflection? It's another type of transformation. And this one, we rotate the object. It's a kind of rotation where the angle of rotation is 180 degrees. And the reflected object is always formed on the other side of the mirror. So we have the object, we rotate it by 180 degrees, and the object is going to appear on the other side. So assume we have a line, then the angle, this angle is 180 degrees. It's going to form a semicircle. That's why this angle is 180 degrees. So our object is going to be to move from this point where we have 0, 0, then you translate or you change it, or this angle this angle that we are using is going to change that or to translate the object, or the object is going to move from this place, the original place, to a different place. And we are saying that it's going to be on the other side of the mirror. So we have the y-axis. If the object is moved on y-axis, so we are going to have our P prime or P1 is equal to the matrix 0, 1, negative 1, 0, 0, 1, then we multiply by P0 or our old coordinates. And when we do this, we are going to get the coordinates for the new or where the object is going to move. We are going to get the new coordinates, and those coordinates, now our object is going to be placed or to be transferred to that area or location. So we have this object, our original object, and we translate or we use this matrix, and our object is going to move to this side. So the other one, so we are saying that the size of the reflected object is the same of the size of the original object. So the size is not going to change. What is going just to change is the location. If the object was in location A, is going to change from that place to a different place. Then the other type of transformation is here. And this one here changes. It changes the shape of the object. The object can be changed along x direction or x axis, or in y direction or the y axis. And we have a matrix. We have a matrix that we use to change this object. Then we come to linear transformation. Linear transformation is a function between two vector spaces that preserves the operation of vector addition and scalar multiplication. As a result, it always maps straight lines to straight lines or zero. Then we have the homogeneous coordinates. What are the homogeneous coordinates? Like now, when we were discussing these types of transformation, we had points. We are saying that we are going to change. We have the old, and we are going to change that to a new, those coordinates into a new coordinates. So like we have this point 0, P0, then is x, y. The coordinates are x and y. When we talk about homogeneous coordinates, we are going to have an extra coordinate. So we have x, y, z. So our P0, we are going to have, these are the coordinates, x, y, and z. So if we are going to have the x prime by multiplied by a matrix, so we are going to have maybe x prime, y prime, z prime. So what do we mean by homogeneous coordinates? We are saying that is another way to present when to simplify the way in which we express affine transformations. Or we can just say that is a represent coordinates in a two-dimension, represent coordinate in two-dimension with a 3 vector, where we have, instead of having only xy, we have xy and we add another coordinate which is w. So add that coordinate to every 2D point. So what are the advantages of homogeneous coordinates? The mathematicians use homogeneous coordinates as they allow scaling factors to be removed from equations. Another advantage is all transformations can be represented as 3 by 3 matrices, making homogeneity in the representation. Homogeneous representation allows us to use matrix multiplication to calculate transformation extremely efficient. Entire object transformation reduces to a single matrix multiplication operation. Another advantage is combined transformations are easier to build and understand. We are through with the transformation. What we were supposed to understand is what we mean by transformation and these types of transformations that we have just discussed. Then the other thing we are going to discuss is introduction to Opengl. What do you mean by, or what is Opengl? An Opengl is a software interface to graphics hardware or the Open Graphic Library. We are saying it's a software interface to graphics hardware. This interface consists of about 150 built-in commands. In some materials, we find that there are 250 built-in commands that you use to specify the objects and operations needed to produce interactive three-dimensional applications. Remember, as we are just concerned on how we are going to draw graphics or pictures on the screen, on a computer screen. So, and we have these commands. We have these commands that we are going to use so that we can achieve, we can be able to draw that picture on the screen. Let me do that. Thank you for reminding me. So we see that in this OpenGL we have some commands. So we have the interface consists of about 150 built-in commands that we use to specify the object and the operations needed to produce interactive three-dimensional applications. OpenGL is designed as a streamlined hardware-independent interface to be implemented on many different hardware platforms. To achieve these qualities, no commands for performing reading tasks or obtaining user input are included in OpenGL. Instead, you must work through whatever reading system controls the particular hardware you are using. So OpenGL doesn't provide high-level commands for describing models of the three-dimensional objects. Such commands might allow you to specify relatively complicated shapes such as automobiles, part of the body, airplanes, or molecules. With OpenGL, you must build up your desired model from a small set of geometric primitives like we have points, we have lines, and polygons. So we have the commands on the OpenGL command syntax. We have OpenGL commands use the prefix GL in small letters and initial capital letters for each word making up the command name, like GL clear color. So we have C in caps, then the other one clear, then we have color, we see in small in uppercase. Then OpenGL defined constant begin with GL in capital letters underscore. Use all capital letters and use underscores to separate words like GL underscore color underscore buffer underscore bit. These are constants. Then we have OpenGL as a state machine. And we are saying that an OpenGL is a state machine. You put it into various states or modes. So you can change the mode of this machine or the OpenGL that then remain in effect until you change them. So if the color is red, it's going to remain in that state or in that mode unless you change the color. So in case you wanted your graphic to be in green and maybe you had set red color and you have not changed, so the graphic is going to be in red color. You can set the current color to white, red, or any other color, and thereafter every object is drawn with that color until you set the current color to something else. The current color is only one of many state variables that the OpenGL maintains. Many state variables refer to modes that are enabled or disabled. With the command, if you want to enable, you can use this command GL enabled or GL disabled. Each state variable or mode has a default value, and at any point you can query the system for each variable's current value. You use one of the six, or we have these six commands to use. So we have G, L, get, boolean, V, you have the get double, depending on your data type. If it's boolean, you use that command. If it's double, you use that command. If your data type is float, you use GL get float V. If it's integer, you use this command GL get integer V. If it's a pointer, the same DL get pointer B, or if you want to enable, you use that. Which of these commands you select depends on what data type you want the answer to be given in. If it's an integer, you use that command. The same to double and the others. Some state variables have more specific query commands, such as GL get right, get error. These are specific commands or specific query commands. In addition, you can save a collection of state variables on an attribute stack with like GL push attribute or GL push client attribute. Temporarily modify them and later restore the values with dpop attribute or dpop client attribute. For temporary state changes, you should use these commands rather than any of the query commands, since they are likely to be more efficient. Then we have the OpenGL rendering pipeline. And this is just a process that our data that we are going to enter is going to be processed. How is it going to process? If we want that shape, maybe it's a rectangle. So this rectangle is going to be processed so that it can appear on the screen. So rendering pipeline is the sequence of steps that the OpenGL takes when rendering objects. Vertex attributes and other data go through a sequence of steps to generate the final image on the screen. So the attribute, these vertex attributes or the points, they are going to, we have some steps that we are going to go through so that at the end of the day we have our final image on the screen. So we are going to look at these stages. So we have geometric data, like vertices, we have lines, polygons. If you see, follow the path through the row of boxes that includes evaluators. These are states. So they are going to be evaluated and per vertex operation, while pixel data, pixel images and bitmaps, series of pixels or series of dots are treated differently. They are not treated as lines or polygons or rectangles like that. They are treated differently for part of the process. Both types of data undergo the same final steps. So if we have a geometric data, is going to be treated differently from the pixel data. But at the end of the day, they are going to come to this final, the rasterization and fragment operations before the final pixel data is written into the frame buffer. Then from the frame buffer, now you can be the picture or the graphics is going to appear on the screen. Let us look at these stages. We have that diagram, we have the vertex data or geometric data, and we have the pixel data, and we are saying that they are going to be treated differently. So we have the evaluator, you can see. Before we come to evaluator, we have the display list, and we are going to look to see what usually happens here. And this vertex data or the pixel data, they are just going to be stored here, but we are going to look at it. Then the vertex data, if it's not going to be stored, comes to evaluator at this stage. Then vertex operation and primitive assembly, if you are going to look at them, then they are coming to rasterization. Then we come to fragment operations. The pixel data, that is for vertex data. If the data is pixel, it is not going to be stored in the list, display list. It comes to these pixel operations. Then from pixel operations to rasterization, or it is not going to go to get to that, it comes to texture assembly, and we are going to see what usually happens in this stage. Then from we have the texture assembly, and now from there the graphic or the text is going to be displayed on the screen. So let us see what happens in this stage. So we have the first one is display list. So let us see when we enter data, like now if the shape is a circle or a rectangle, what is going to happen, so that at least we are going to see it on the screen, because that's what we draw. Maybe you want to draw a circle or a rectangle. So, and these are the stages that our data is going to go through. So, we enter the data if it's either vector or pixel. All data, whether it describes geometry or pixels, can be saved in a display list for current or later use. If it's not going to be processed, it's going to be stored in the display list. The alternative to retaining data in a display list is processing the data immediately. If you're not going to store the data is going to be stored to be processed. Maybe you want the data to be processed immediately, also known as immediate mode. When a display list is executed, the retained data is sent from the display list just as if it was sent by the application in the immediate mode. So it is not going to be stored in the display list. It's going to go to the evaluator. If you can remember, you have that diagram in your head. You can see it. Let me just go back to, so you can see where the elevator is. And let us see what usually happen in that stage or in that place. All geometric primitives, like the rectangle, lines, polygons, are eventually described by vertices or points. So if it's a rectangle, it has 3 points. Maybe we can have point A, point B, and C. Parametric curves and surfaces may be initially described by controlling points and polynomial functions called basis functions. Like those points, we have 3 points, A, B, C for the rectangle. Evaluators provide a method to derive the vertices used to represent the surface from the control point. The method is a polynomial mapping which can produce surface normal, the texture of that shape or that picture or graphic, color of the object, and spatial coordinate varies from the control point. So after evaluator, so we have those points. So we have point A for the rectangle, B and C, or these points or the vertices. Then after that, we come to per vertex operation. For vertex data, next is the per vertex operations stage, which convert the vertices or these points into primitives. Then after per vertex that converts the vertices into primitives, we come to primitive assembly. So we have this coordinate for the rectangle. We have A where we have that vertices on this pattern. We have the other one like that. So they have been collected. Then we come to primitive assembly. And these are what usually happens in this place. Clipping, what we mean by clipping, we have a topic on that, is where so we have our rectangle. We have the coordinates or this um, yes, we have the world coordinates or the world system coordinates, like the way we have this we have x-axis and y-axis, and we want to have or maybe let me just give an example of our screen, because we have that. So we have the window or this screen. Remember, we even discussed where we have where the picture is going to appear, what we are calling the screen size. Let me use that. We have the screen size and we have the outer piece, the other part where we don't have the screen. So we have the outer piece and we have the area where the image is displayed, or where you can see the slides. So when we come to, we are saying that clicking, so we have our rectangle on the screen. Then we want to remove some parts that we don't want to appear on our screen. So we have that rectangle. Remember, it has gone through transformation, and there are some parts that we want to remove from our picture so that we only have our rectangle. Maybe to get not rectangle, our triangle. Maybe to get this triangle, we had the original object was a rectangle or a square. Using that square, we want to create or to come up with that rectangle. Sorry, not rectangle, triangle. So we are going to have a window, and that window is going to help us to shape or to come up with that shape of the rectangle. And now, because we have now our rectangle, we have drawn our rectangle using the window. So we are going to have some parts of our original rectangle. So we are going to remove those unwanted parts, and that's what we are calling the clipping. So when we come to primitive assembly, we are going to remove the parts of our triangle that we don't want to appear on the final object or our final image. So clipping, a major part of the primitive assembly is, or the clipping is the elimination of portions of geometry which fall outside the half space defined by a plane, or what I'm calling the window. So we have that plane. So we can have point clipping. We'll come to this. We have different types of clipping. So we have the point. Remember, our triangle have point A, point B, and point C. When we come to point clipping, we are going to remove the points that we don't want, or there. So we have then the line. We have drawn the line where we want where we have the line that is separating the part we want and the part we want to discard. So when we are having our points, there are those points that they are going to lie on the part that we want to remove and the part that we need, the wanted part and the unwanted part. So these points that are on the other side that we don't want, we just remove them. And how are we going to remove them? We are going to use point clipping to remove these points that we don't want, and be left with the point that we need. Point splitting simply passes or rejects vertices. Line or polygon flipping can add additional vertices depending upon how the line or polygon is going to be flipped. Then after primitive assembly, we have seen is just removing the unwanted parts that we don't want to appear on our final image. Then we come to the pixel operations. While geometric data like the line, polygons, rectangles, it takes one path through the Opengl rendering pipeline, a pixel data takes a different route. And from our diagram, we can see that. Let me go back to our diagram. So this is the vertex data is following this route, and this is our pixel data, and is following the other route. So from this we come to pixel operation. But vertex data comes to this stage where we have the evaluators, so that we can pick the point that we want to appear on our image. Like now we have the triangle. So we have point A, point B. So we pick or we collect those vertices or the point that we want to our object to have. So if the data was pixel data, is not going to go to the evaluator, is going directly to the pixel operations. Let us come to pixel operation or operations, while geometric data takes one path through the Opengl rendering pipeline, pixel data takes a different route. Pixels from an array in system memory are first unpacked. So they were packed, now you unpack them from one of a variety of formats or shapes into the of components. Next, the data is scaled and you process that data, process and mapping and fronting are then these results are packed into an appropriate format or shape, the shape that you want, like we want the shape to be triangle, and returned to an array in the system memory. So those packed, the packed result or shape, the shape that we want is going to be stored or taken back to the system memory. Then after pixel operations, we come to texture assembly. And here we just want to make that graphic or that picture to look real. If it was a ball, it's going to look like a real ball. If it's a car, it's going to look like a real car. So let us see. An OpenGL application may wish to apply texture images onto geometric objects to make them look more realistic. If several texture images are used, it's worth to put them into texture objects so that you can easily switch among them. So we have rasterization. Rasterization is the conversion of both geometric and pixel data into fragments. So Rasterization is where if it's a vector graphic, you are going to convert that into, into pixels or dots. Remember I said that the pixels, they are squares. These squares, so those are vector graphics, like we have the polygon, the rectangle, you are going to change them into raster format. Each fragment square corresponds to a pixel in the frame buffer. Line and polygons equals like line width, point size, shading model, and coverage calculations. To support anti-aliasing are taken into consideration as vertices are connected into lines, or the interior pixels are calculated for a fifth polygon. Color and depth values are assigned for each fragment square. Then we have fragment operations after rasterization. Before values are actually stored into the frame buffer, a series of operations are performed that may alter or change or even draw out fragments. All these operations can be enabled or disabled. The first operation which will be encountered is texturing, where a texture or texture element is generated from texture memory for each fragment and applied to the fragment. Then the other one, after you put the texture, so that then the picture is going to look like it's a real object, then we come to the then flow calculation. What do you mean by flow calculation may be applied? In flow calculation or calculations, this one we just add some to add realism to a computer generated scene. So that object. So we do some calculation, and here we have some programs that we use. Like we have the vertex Fedra. It's just a program that we are going to use so that we can be able to put that texture, so that the system, or not the system, the object that we want to create or to draw is going to look like it's a real object or real picture. So we have these calculations, and still this is done by this program, so that we are able to come up with that texture, or the picture or the graphic to appear like it's a real picture. And the sister test is where you just remove some unwanted fragments, like the way we have seen that you click to remove some uh, unwanted points or parts of the object. Then we have the alpha test. We have the uh, cent- cent- centile test, and this is where you just have a value. You just want to compare. You compare the object that you want to, or the image that you want to appear on the screen. You use this value to see whether it has come the way you want it to appear, or it appears the way you want it to appear. If it's that triangle, so we are going to have some test. And how are we going to test it? We are going to have a value. So maybe we have another, we had created a triangle. So we are going to use that triangle to check whether the new triangle we have drawn or we have created is similar or is the same. Then after that, we have the depth buffer test. The depth buffer is for hidden surface removal. Then, if an enabled test may add the continued process of fragment square. Then, blending, dithering, logical operations, and masking via bitmap may be performed. Finally, the fragment is drawn into the appropriate small boxes, what we are calling the pixels. You know, that's why we are converting all from vector graphic to raster graphic so that it can appear on our screen. So that data was the data or the graphic or the picture that you want to appear on the screen. Then we have OpenLG related libraries. So we have the GLUT is the Open GL, the Graphic Library Utility Toolkit. A within system independent toolkit for writing OpenGL programs. It implements a simple windowing application programming interface for OpenGL. GLUT makes it considerably easier to learn about and explore OpenGL programming. The other library is GLX, is used on Unix OpenGL implementation to manage interaction with the X window system and to encode OpenGL onto the X protocol stream for remote rendering. Then we have the GLU, is the OpenLG utility library. OpenGL utility library. This is a set of functions to create texture, bitmaps from map, base image, map coordinates between screen and object space, and draw quadratic surfaces and nuts. Then we have DRI, is the direct rendering infrastructure for coordinating the Linux kernel X window system, 3D or three-dimensional graphics, hardware, and an OpenGL-based rendering engine. So we are through with the OpenGL, and we come to coordinate system. These are just terms, and we are going to look at them. We will come to this later, or maybe we are going to encounter them somewhere else. So let us just see these terms. Coordinate system. This is a term, and we are saying that it is a system which uses one or more numbers or coordinates to uniquely determine the position of a point or other geometric element. Like the way we have our, we have point P, and these are the coordinates x and y. The order of the coordinate is significant and they are sometimes identified by their position in an ordered tuple and sometimes by a letter, as in the x coordinate. Then we have the y coordinate and x coordinate. Then we have world coordinate system. The world coordinate system contains the simulated world, that is the scene to be rendered. In other words, represent a coordinate system in given units that represents a given application program of the world, also known as the universe or sometimes model coordinate system. And this is when I was explaining how to create or how to remove some the wanted parts of an object. I said that we have the plane or what we are calling the window. Maybe you have that rectangle or the square, and from that square we want to come up to create or to come up with that triangle. So we are going to place a window for the triangle that we want to create. And when we put that plane, so that's what I'm calling the window. And it has the coordinate, what we are calling the world coordinate system, or the window coordinates. And using that window or the plane, now we can be able to, the parts that are uh, uh, beyond our window, we are going to remove them. So we have the window coordinate, what we are calling the world coordinate system. After we remove those unwanted parts, now we are going to have our triangle. And then after that, we are going to have the viewport, and we are going to come to that. So the world coordinate is what I'm calling the window, that plane that we are going to use so that you can be able to uh, have the part that you want and those parts that you don't want. This is the base reference system for the overall model, to which all other model coordinates relate. Then we have the Cartesian coordinate system, and this is not unique to us. Specify each point uniquely in a plane by a pair of numerical coordinates. Maybe 0, 0, the origin is 0, 0, x1. Um, from the point to two fixed perpendicular directed lines measured in the same unit of length. Then another term is screen coordinate system. The grid or bitmap a computer uses to turn monitor pixels on and off. This 2D or two-dimensional coordinate system refers to the physical coordinate of the pixels on the computer screen based on current screen resolution. Remember when we were discussing our output device like the monitor, we see that we had these terms like the screen or the physical what do you call it? The display. And we say that we can still call it the screen size or the display size. And that's where the part that the graphic or the picture is going to appear. And we are seeing that or the number of pixels for that screen or that monitor. So we are saying that this 2D coordinate system refers to the physical coordinates of the screen size, the number of pixels that are in that screen or the size of the screen. Object coordinate system. When each object is created in a modeling program, the modeler must pick some point to be the origin of that particular object. Like now we can take the origin is 0, 0, x, y is 0, 0 of that particular object, and the orientation of the object to a set of model axes. For example, when modeling a desk, the modeler might choose a point in the center of the desk, the desktop. So we have that desk or the service or the place where you have placed your laptop. So you can have the origin or just a point, what we are calling the object coordinate. So we are saying that at that desk that maybe you have placed your laptop, a center of the desk, the center of that desk, you can have that point, and that we can call it the origin or uh, the desktop for the origin. Or the point in the center of the desk at a floor level or the bottom of one of the legs of the desk to be the origin or the origin point. Maybe it could be 0, 0 or 1, 1. When this object is moved to a point in the world coordinate system, and I have explained what we mean by world coordinate, it's really the origin of the object in object coordinate system that is moved to the new world coordinate. And all other points in the model are moved by equal amount. Then we have the hierarchical coordinate system. The hierarchical coordinate system, sometimes objects in a scene are arranged in a hierarchy, so that the position of one object in the hierarchy is relative to its parent. Like the way we have the parent, we have that node, we call it a parent. Then under that we have other nodes, these nodes. So we are going to have three nodes. We have the parent node, then we have two other nodes from the parent, and we can call them the child. The other node, we can call it a still child. So we have the parent and the children. And when we have such, so we have the parent and we have other nodes below that, we form that hierarchy or that structure of one object in the hierarchy world coordinate. For example, we have a heart may be positioned relative to an arm, and the arm relative to the torso. When the arm moves, the heart moves with it. And when the torso moves, all three objects move together, because it's like they are connected. So we have the child, the parent, and we have the children, and whatever you do to the parents is going to affect the children. Viewpoint coordinate system. So we have seen what we are with the window system, or that frame that we are going to use so that we can draw our object. So viewpoint coordinate system, so we are going to come up with that object that we want to appear on the screen. We're going to have some points or the coordinates. So the window has these coordinates, and the whatever the object that we are going to create is going to have some coordinates. So we have viewpoint coordinate system, also known as the camera coordinate system. So when we click or we remove the unwanted parts, now we are going to be left with our triangle. And that triangle, it has some points, like we have point A, B, and C. And that's what we are calling the viewpoint coordinates, the coordinate of our object that we have created. This coordinate system is based upon the viewpoint of the observer, and changes as they change their view. Move an object forward in this coordinate system moves it along the direction that the viewer happens to be looking at the point. So you can move from this point, and now you are going to have the viewpoint coordinate when you change the position the same. So, and still we have other terms, like we have the viewpoint coordinates, then we have the viewport. And the viewport is the area on the screen where the our object is going to appear. It can fill the whole screen. It can be on the center. So if that place on the center where the object is going to appear is what we call the viewport. It can appear at the top or even at the corner. That place where the object appears or is going to appear is what we call the viewport. Then we have model window coordinate system, not to be confused with the desktop windowing system, into bracket MS Windows or X Windows. This coordinate system refers to the subset of the overall model world that is to be displayed on the screen. Like the our viewport, that whatever I was explaining. So we have our world coordinate, then we have our view coordinate, and so we have a model with the coordinate. And then our points, our new points. Let me call them the new points that are going to, where they are going to appear. The viewing parameters selected, the model will be the linear or distorted viewing frustum of the same type. Then we come to the viewport coordinate system. This coordinate system refers to a subset of the screen space. Na nimesema is that the part or the portion where our object is going to be displayed or to appear, where the model window is to be displayed. Typically, the viewport will occupy the entire screen window or even the entire screen. But it also possible to set up multiple small within a single screen window so that it can appear anywhere on the screen. Maybe center, uh, at the corner, top, bottom, or on the side. But that place or that space where the object is going to appear is what we are called the coordinates. We are calling them the Viewport coordinates. And that's all what I had prepared for today on transformation um, and on OpenGL. Unless there is any question, you are going to get these notes through our class representative. And uh, next week, we are going to have our first cut. We are going to have our first cut. Yes, unless maybe there is any comment, we can stop at that point. You can comment, you can add, or you can even have a question on what we have discussed on transformation or open details. If there is no question, you can call it a day.